In this video, we will provide a complete overview of the new dynamic reverb system. The new system is of better quality, has lower performance costs, and is easier to customize than the old version. You can try the new demo by using a link in the description below. You don't have to watch the previous reverb tutorials before watching this one. We divide this video into 3 main parts. Firstly, we'll show you how to set up your project to work with the plugin. Then, we'll quickly review the new reverb flow. And finally, we'll discuss customization options and future improvements. Now, let's get started. As in the old version, the reverb system is centered around our modal spatial interface. HRTF stands for Head Related Transfer Function, which is used to create 3D audio for headphones. The enclosed factor shows how much of the room is covered. In an empty outdoor scene, its value is 0. On the contrary, in a room without doors or windows, its value is 1. I will explain this in a parameter later. It's a workaround to fix a long-standing problem of MetaSounds interfaces. Open room measures the complexity of the room. And finally, room size is the cube root of room volume. This interface provides information about the current scene surrounding the player to all graphs that implement it. To allow the interface to work correctly, there are 3 steps you have to follow. Firstly, please set the source data override plugin in your project platform settings to modal spatial. For example, in Windows. We change this to modal spatial. If your project supports other platforms, please also set them to modal spatial. Secondly, you will need to enable source data override in your sound attenuation settings file. We also provide an example file here. All you have to do is enable this. Note that in a real attenuation file, you should also enable this. So Unreal won't spawn graphs outside of the specified range. We don't enable this in the example file because it isn't a requirement for our plugin to work. Also, you are not meant to directly use this file in your project. A real project will have multiple sound attenuation files for different types of sound effects. You must also set your MetaSounds graphs to use an attenuation settings file that is source data override enabled. Finally, in your player character, add a dynamic reverb component. This component is responsible for scanning the scene around the player at runtime and update modal spatial interface data. And that's all you need to do to set up your project for the plugin to work. Since we are already here, I will explain important parameters of this component. The first 2 parameters are for HRTF nodes. It's this node inside our reverb graphs. If you enable HRTF, this parameter will be 1 at runtime, regardless of the value set inside the graph. If enabled, this node will add a 3D effect to the input audio based on its location in the camera location. It's intended to be used for headphones. On speakers, the effect is barely noticeable. For more details about the algorithm, please take a look at our HRTF video. If you disable HRTF, this node will become a simple stereo pattern node. Head radius is a static variable used inside our HRTF algorithm. 0.2 should work well for most people. The tracing section is where we store all parameters for scanning the scene around the player. Each time we trace a scene, we actually use 8 single line traces, each is fired in a semi-random direction. We use async traces here to avoid blocking your game thread. And the trace frame is finished only if we have received results from 8 asynchronous line traces. This trace tick controls how many traces are done per second. By default, we trace the scene 30 times per second. Again, each trace frame fires 8 synchronous line traces, and a new trace frame can only be run after the last one is finished. So this won't affect your game performance. The trace channel is a collision channel used in line trace. The default is set to camera, but you can also create a specific channel for reverb to control what objects will reflect sounds. Up, down, and trace pitch offset control the pitch randomization range of each trace. They are set based on real testing. You normally don't need to change them. We might hide them in future updates. The number of interframe controls how fast all data of the modal spatial interface changes after each trace frame. Because the tracing is randomized and the player is constantly moving, the data is very noisy. This works like a moving average window to smooth things out. In the old version, we used a very simple method to measure room size and enclosed factor. But in this version, we've implemented a more advanced method which provides greater details about the room. It's more accurate, more stable, but also has a slow converging time. If you disable this, the old method is used instead. The trace end vector determines the end location of a line trace. Only the X channel is used. 10,000 means 100 meters. High offset allows you to adjust the height of the start location. To make it easy to understand, I will set this to true, and run the demo. So the starting location is the center of the capsule. These sections allow you to visualize and monitor the tracing process. Room mapping will draw a box using the measured X, Y, and Z coordinates of the room. Box map shows all the current stored mapping points. This prints out all measured results in the output log window, and this logs out warnings or errors of the process. Let's run the demo a bit to see how the tracing process is done. If you press R, the demo will enable the room mapping debug option earlier. These two lines are the X and Y orientations of the room. Pressing it one more time, all current mapping boxes will be shown. In the new method, each sampled collision point from the scene is quantized into a 2-meter box. To adapt to players' movement and dynamic scene changes, each box has a lifetime. Their lifetime is calculated based on the number of interframes. Each time a collision point inside the box is sampled, we refresh its lifetime. If a box has reached its lifetime, then it's deleted from the map. So the reason you see this yellow box keep changing is because old boxes are deleted and new boxes are added. It might seem a bit scary when it keeps varying like this, but we only care about room size, enclosed, and open factor. So the changes in the center point as well as its direction are not a problem. If you want it to be more stable, you can increase the number of interframes. But doing that will also make the algorithm adapt more slowly to the scene. Also, storing more points will make the algorithm run slower. The average running time of the new method, with default parameters, is around 0.4 millisecond, measured on Intel IF of 3.2 GHz. It's a 10-year-old CPU in case you want to know, so it won't have a major impact on your game performance. Notice how these parameters change when I move to different rooms. If I stay a bit longer, the enclosed factor gradually converges to 1. Because the box size is 2 meters, these pillars make the uncovered parts look like they occurred. Smaller box sizes will improve the resolution, but they increase the processing time and adaptation speed. The 0.9 to 1 range is not noticeable, so we chose 2 meters to be a good trade-off. Now, near the entrance, the size is still large, but the enclosed factor is smaller than inside the room, even though we are still in a completely indoor environment. This is a major change compared to the old method. Enclosed factor is like saying the measured size is this big, but there are uncovered parts, so the size of the scene is actually bigger. Now, I move a little bit like this to make the measured results noisier. The height measurement has a hard time choosing between the ceiling of the room and the tunnel. To counter this, you can see the changes in the open room factor. See how it's lower when the ceiling of the room is chosen. Open room factor is like saying the measured size is this big, but there are objects in the way. This makes the reverb more stable. So we have different impulse responses at the entrance, the middle, and at the exit, which is the intention of our reverb system, to emphasize the perception of the scene around the player through reverb. If you turn this off to use the old algorithm, you will see it adapts faster, though it's noisier. The open room factor is always 1 because we can't measure it using the old method. Let me turn this on again and run around a bit. Another change compared to the old version is how we do reverb for outdoor environments. Before, the reverb isn't hearable if the enclosed factor is below 0.5. Now, thanks to the new reverb node, the effect of wind is included. We can create very long outdoor reverbs without metallic artifacts. You can change the reverb loudness in the demo by using the Z and X keys. With Reverb, and without Reverb. With Reverb, we have a better perception of the location. This places the empty outdoor environment we are talking about. The more empty a scene, the harder to measure accurately. You would think it's the reverse, but if a scene has many props, we have more collision points to map the room. By the way, the algorithm limits the measured size to 64 meters. Above 64 meters, the differences in reverb are barely noticeable, so we choose that size to optimize the algorithm. This scene shows the current weakness of our methods. This is also true for the old one. Because the origin of each trace is centered at the player, it can fail to measure the enclosed factor for places like this, where the roof is too wide. Again, an enclosed factor of 1 means the algorithm thinks this location has walls around it. This makes the reverb longer and louder than it should be. Not a major problem, because it's not completely wrong, but we think you should know about this limitation. There is a way to fix this problem by setting the interface data manually. I will show you how to do that in the customization section. The room direction changes abruptly because the size is square. It only has meaning if the room has a rectangular shape. We do not use the direction for now, but it's intended for some future usage. Like if we detect a narrow but very long room, then we can add echo effects to make it even more realistic. That's one of many things we're considering for version 3.0, but I can't say for sure. It might be better if we just let you manually set special effects for specific scenes. Now let's take a look at reverb graphs. We will use a pistol graph as an example. If you look into the ranged weapons SPF folder, you will see that we have two pistol graphs. One has an additional G, this is the one we use in the demo. But let's start with this one first, because it is easier to follow. The dynamic reverb HRTF node has been completely changed compared to version 1.0. Before we go into this, I will have to explain this play event first. If you look into all SP graphs, you will see we gate the onPlay event using this setup. This control by float node will pass the trigger if its input value is higher than 0.5. Or when the running time of this graph is higher than the wait time. This is done to make sure the interface data is properly initialized before running. This applies to all interfaces, including the default ones from Unreal. To illustrate this problem, I've prepared a simple distance attenuation graph. It uses the distance attenuation interface of Unreal. I use a mapping node to convert distances above 5,000 to 0. I also print out the distance so we can track in the log window. Here is how it sounds at 0 distance. Now I will play it repeatedly inside the scene by using a simple 3D sound repeater. Gonna place it far away. If everything works correctly, you should only see one value of distance, and you won't hear any sounds because the distance is higher than 5,000 centimeters. Occasionally, you hear some pop noises, and looking at the output log, you'll see some 0. This means the distance is not initialized before the graph is run. It works correctly 80% of the time, but the remaining 20%, when it won't work, will cause a problem like this. This is an issue for all MetaSounds interfaces, likely because the interface data is passed from the game thread asynchronously. It's a long-standing issue and still exists in Unreal 5.5. Granted, it's not something easy to fix. A workaround is to use a console command to force MetaSounds to run on your game thread, but that will affect your game performance. Another way is to use attenuation settings files for distance and spatialization. You can hide the problem by reducing the gain right in the settings file, but this removes the customization ability for reverb and spatialization inside the graph. So we implemented this parameter in this node to gate on play event. It works reliably and costs next to nothing. But it is not an elegant solution because you will have to add it manually to your graphs. If we gate it inside the reverb node, the first few frames of your audio will be ignored. The setup is simple, just connect onPlay event to this, and the init parameter to the input value. Then use the output to trigger the play event of your nodes and the reverb node. Just remember that you should never change this parameter by yourself. Always keep it at 0 inside your graph. If you set it to 1, the gate is bypassed. Now let's dive into this node. Compared to the old version, the new flow is more similar to algorithmic reverbs. Instead of using a simple delay node like before, an early reflection node is used to delay the input and do some light filtering for distance attenuation. One of the outputs is then passed through to a diffuser node to create early reverb. The other is passed to a late reverb node. The number of reflections determines how many times the input is repeated in the output. The delay time of the first reflection is controlled by the earliest reflection time. The delay time of subsequent reflections is calculated based on the room size and open room factor. Each reflection is filtered by using the number of modals specified here. This clamps the maximum delay time of all reflections. Fmax is the maximum frequency we will sample from the input signal. The refresh period controls how we update all the input parameters below it. If it's 0, changes to these input values when the node is running will be ignored. For example, one shot sounds like a gunshot will set this to false, so reflection calculations aren't changed when running. Continuous sounds like music will set this to true. So, reflection timing and its filtering will be updated every 20 milliseconds. Distance attenuation is supported by using modal filtering. Loudness and high-frequency signals are reduced over distance. You can scale the reduction speed by using this distance scale. If you want to hear faraway sounds, you'll need to reduce this down. The modal reverb node in version 1 is now replaced by a modal late reverb node. It's much easier to use and runs 1.2 times faster. Instead of controlling the number of modals in each frequency band to optimize the performance, you can now simply choose the maximum frequency of your input audio. Fall-off scale controls the fall-off rate of reverb over room size and enclosed factor. For sound effects like footsteps or melee weapons, you might increase this to 1.5 to reduce the duration of reverb in large rooms or outdoor environments. For explosive sounds like gunshots, you might reduce it to 0.75 or 0.5 to make the reverb longer. Diffusion scale controls how early the result sounds. One major improvement of this node is that it can simulate the effect of wind on reverb, and this input controls that fact. The old reverb node can't simulate outdoor reverb or rooms larger than 50 meters. But this node doesn't have those limitations thanks to wind simulation. Reducing this will make the result sound heavier. It is clamped internally, so the wind effect is always simulated. You can't turn it off by setting this to 0. Decay min clamps the minimum reverb decay rate. Increase this if you don't want a long reverb duration. Scaling late reverb loudness over distance inside this node uses a non-realistic equation. It is done so that faraway sounds will have lower loudness and much shorter reverb duration. If we scale it like in the real world, then it will be overly noisy. Especially in shooting games, hearing full reverb of gunshots from enemies 50 meters away isn't great. In video games, you want to put more emphasis on sounds closer to the player, so the player can react to nearby events. Let's test this distance scaling in the demo. The further, the shorter the reverb, even though the room size, enclosed, and open factor are the same. Late reverb is very important to create the perception of depth. If I turn it off, you'll feel like the sound is nearer. One more thing about distance attenuation inside reflection and late reverb nodes is that sounds outside of the room are scaled down more aggressively. This means not only the gain, but high-frequency signals also decay faster. The reason is that if the room size is smaller than the distance, we know there are obstacles between the source and the listener. So, an occlusion effect is added to further reduce the loudness. Spatialization is done separately. For late reverb, a simple stereo panner is enough. It also quickly converges to the center to make it directionless. Direct sounds, early reflection, and early reverb allow 3D spatialization with HRTF if it's enabled. This audio input is meant for close proximity layers, which don't have reverb, but still need spatialization. Let's take a quick review of important inputs. Final gain allows you to scale the gain of all layers, so you can quickly adjust the total loudness. Gain dry is the gain of these two inputs without reverb. Distance gain scales allow you to change the gain reduction rate over distance. A value lower than 1 will allow you to hear far distance sounds more clearly. Early reflection gain is the gain of early reflection and early reverb. Most of the time, we keep the number of reflection at 1 and early reflection time at 10 milliseconds. For loud sound effects like a gunshot, you can reduce the fall-off scale to make the reverb last longer. For things like footsteps, you can increase this to make them hearable indoors, but fall off faster in outdoor locations. The advantages of implementing reverb per sound are that you can easily preview it and adjust parameters accordingly. However, it has performance drawbacks. While our method doesn't require too much memory like algorithmic reverb or heavy calculations like convolution reverb, you still might want to do the reverb globally instead of per sound source. So in this update, we also support global reverb directly. Graphs that use global reverb are prefixed with GSPA. Let's take a look at the GSP epistle graph. It's very similar to the other one. This early reflection node will route its output to an audio bus for global reverb. The flow is also very similar, but the late reverb node here is removed. To support distance attenuation, a distance to gain node is used here. This node uses the same gain reduction equation as the late reverb node. We write both the left and right channels to the audio bus. And here is the global reverb graph. It's extremely simple. By using an audio bus, all sound effects are merged, and their late reverbs are generated simultaneously. So, whether you play 1 or 10 sound effects, the cost is the same. This also allows us to use different nodes for the left and right channels, which will produce better results because it decouples the left and right ears, making late reverbs feel wider. To use this graph, simply add it to your world. All the sounds used in the demo use global reverb instead of per sound source. Though doing reverb globally, we can't change its parameters per sound source. Using the same settings for all types of sound effects usually isn't good enough. A workaround is to create separate global reverb graphs for different types of sound effects. You'll just have to duplicate this. And add a new audio bus. Then you can change the fall-off scale or other settings for your targeted sound category. To achieve the best balance between performance and customization, you can use both global and per sound reverb. For example, you can use 2 global graphs to cover most of your sound effects. Then, for some special effects, you can use reverb per sound source. Most of our graphs in the plugin implement reverb directly. This is because we want to show you how to adjust parameters for different types of sounds. And it's easier to preview them in MetaSounds. But in a real project, you should use the global reverb flow for better quality and lower performance costs. On the topic of customization, aside from tuning the fall-off scale and gain, you can control the reverb by modifying the interface data before passing it into the node. For example, if you want the reverb duration to increase more slowly with the room size, you can do some mapping like this. I keep the size below 10 meters intact because the reverb is already short. You can tune the range and the reduction rate to fit your requirements. If you know all your scenes are neither empty nor closed, you can clamp the enclosed factor. Like most scenes have an enclosed factor between 0.2 and 0.85. Lower than 0.2 makes the reverb nearly inaudible. Higher than 0.85 can make the reverb duration a bit longer than necessary. Thanks to MetaSounds graphs, it's very easy to modify the system to suit your needs. Now, what if you want to manually set these values for some specific locations? It might be because you want some specific parameters in certain places, or because the algorithm has trouble analyzing the current room. Then, you can use the entering method of our dynamic reverb component to set these values from your blueprints. For example, I can use a volume trigger here to manually override room stats. I will set this up on the level blueprint. Again, room size is the cube root of room volume. For enclosed factor, if it is completely closed, like in an elevator, set it to 1. If the location has no roof, subtract the enclosed factor by 0.35. Then, if it lacks some left, right, front, or back walls, each missing wall will reduce the enclosed factor by 0.15. Since you've already set the room size directly, you can keep the open room factor at 1 for simplicity. Once you call this function, the component will still trace the scene, but it won't calculate these parameters. To enable automatic analysis again, you need to call the exiting function. These parameters will be used to initialize internal buffers, so the algorithm can adapt faster to your scene. So if you only want a fast change, you can use this function without calling the entering one. And that's all you need to know about the new reverb system. Compared to version 1, it has much better reverb quality, high accuracy, and more customization options. Currently, the reverb is colorless, meaning we don't include special settings for materials like wood or metal. And as mentioned before, we want to include more echo for some special room shapes in outdoor locations. Those are the things we are considering for future updates. But they won't happen anytime soon, because there are some other parts of the plugin we want to improve first. The next video is about an extremely useful node added in the upcoming update. It will generate distorted textures for your audio. I believe you will find it useful to enhance your sound effects. Bye for now.